Okay, I'll be sharing screen. Mm. So we are back into course here. Let me move this there. Okay. So chapter 2. So this is the outline of the course. So you see, there's a lot of topics. There are lots of topics to cover. We only did the introduction to radiative transfer, and now we'll be looking at the propagation of electromagnetic waves, um, which is to say, to describe how electromagnetic waves propagate inside a medium. We need to know how to calculate the absorption coefficients and the emission coefficients, and this is what we'll be describing in chapter 2. Chapter 3 will be dealing with the radiation sources, and then for the rest of the course, it's about the rest of the course is focused on specific examples of microscopic processes leading to radiation. Electromagnetic wave propagations. So first is generalities on electromagnetic waves and where do they come from. Then we'll see the propagation of waves in vacuum. And then we'll look at something that should be new to you, which is the wave propagation in a medium. In principle, these are things that you've already seen, except the third section. You might not have heard of the relationship that exists between the refractive index. In the refractive index in a dielectric, it's got two parts. It's got a real part and an imaginary part, and these two parts are related by the Kramers-Kronig relationships. You might have seen all of this, so I really do not want to bore anyone. So if you want me to speed up, just say so, okay? But we just need to summarize this and make sure we've been through it. So these are the Maxwell equations in vacuum. No, that's with sources. So this is in a medium. So that depends on the electric displacement vector, the electric field, magnetic field, and the magnetic induction. Well, it depends. Those names depend on a bit on which textbook you're following. It's common to relate D and E with with this relationship. From memory, I think these are constitutive relationships. They call like that. Let me fix the typo back here. And so in vacuum, these constants are just the electric permittivity of vacuum and the magnetic permittivity of the vacuum. So the electrodynamic potentials are well similar to the case in electromagnetostatics. We introduced the potential vector this way, and we inject this equation into equation 3, which is that would be the law of induction. And so if we inject a B equals nabla cross A into equation 3, we get this other expression where we have the curl of this expression always equals to 0. And this, in other words, means that whatever is this expression, it's a gradient. It can be written as a gradient. And so we relate the electric field with the electric potential corrected for the vector potential. Is this new to anyone? No, okay. So what I want to do is calculate the electrodynamic potentials, and to do so, we've used the Maxwell equations in vacuum, and we replace the expressions for E and B. So, for instance, this the Gauss law gives us well, this other expression that connects phi and A simply by replacing E with equation 6 here. So I use equation 6 and I inject it into the Gauss law to reach this this intermediate equation here. And then we use the Ampere-Maxwell equation, which is the other Maxwell equation. And we replace B and E by their expressions in terms of A and phi. And we then reach equation 8, which is almost like a wave equation, except for this gradient here. So this is the gradient of this expression, which we might call the Lorentz term, if you want, okay? And so if this Lorentz term is 0, then both phi and A fulfill wave equations with a source term, okay? So of course, in general, A and phi do not fulfill the Lorentz condition. In general, this condition is not always met. However, we will be using the freedom of gauge to find A and phi such that equation 9 is fulfilled. So this is a bit subtle. I'm sure you've heard of it before, but it's important to make sure that this is clear. The idea here is to add this the gradient of this gauge term lambda. So we add this this gradient to A, and since B is defined by the kernel of A, whatever gradient you add to A will leave B unchanged. Okay, so this transformation leaves B unchanged, but of course we need to correct also for the impact on the electric field. So if I change A here with the addition of a gradient, I'll be changing E too. Okay, and so for E to also be preserved, to you know, so that E is invariant, we also need to correct the electric potential. So this is the freedom of gauge. We can change A by adding a gradient of this field lambda, which depends on position. But if we do so, we also need to change the electric potential by correcting with the partial derivative in time of lambda. So this allows us to modify A and phi and search for A and phi, that search for lambda, so that A and phi fulfill equation 9. Okay, so that's the idea. In order to find this lambda, we inject then the equations we've just seen. So equation 12 and 13 are these freedom of gauge equations. So we replace A by, so equation 9 is the Lorentz condition, okay? And suppose I write this equation 9 in terms of the primes. So the divergence of A prime plus 1 over C squared, the time derivative of phi prime. Okay, so I've written it in terms of the primes, okay? And then I use equation 12 and 13 inside this Lorentz condition. So I replace A prime by A plus nabla plus the gradient of lambda, and I replace phi prime by phi minus time derivative of lambda. If you do that, then you end up with this equation, equation 14, okay? So this is the Lorentz condition with the freedom of gauge. So including this lambda term, where I've added the terms including lambda. And this part here, which affects lambda, is the wave equation itself with the source term. That would be the source term. I mean, we're saying we have A, we have the vector potential, we have the electric potential, but they do not fulfill the Lorentz condition. Okay. In order for them to fulfill the Lorentz condition, I need to find a lambda that will allow me to do this freedom of gauge and make them satisfy the Lorentz condition. And this lambda is given by this equation. So we need to find a solution to this equation. Okay. And in this equation, this term here is a source term. It acts like a source term. I could move it to the right-hand side, and you will see that it's like a source term, and this is the wave equation. Okay. And this is exactly the type of equations we're trying to solve at the moment. We want to eventually do radiation, which is exactly this, solving the wave equation with the source term. Okay, so we'll admit that waves exist with a variety of forcing terms. So whatever A and phi, this is just going to be a field of position and time, and this is going to lead to some lambda, and so we can indeed find the lambda that will make A and phi fulfill the Lorentz condition. So without loss of generality, we can assume that A and phi always fulfill the Lorentz condition, and are then solutions of the wave equation. So this is you can imagine how the complexity of these of electrodynamics you can imagine the complexity of electrodynamics here. If you do it the brute force way, this is the brute force. You know, we need to find A and phi so that they are solutions of these of the wave equation given the forcing term J and rho, the electric density. Okay. And make sure also that A and phi fulfill the Lorentz condition. Okay, so that's if they do not, then we need to do the freedom of gauge and find lambda so that they do. Okay, now independently of the electric potentials, you can also manipulate the Maxwell equations to reach the wave equations in the electromagnetic fields. So this is the wave equation for the electric field, and this would be the source term for the electric field. Likewise, for the magnetic field, we also have a wave equation, and this would be the source term for the magnetic field. So, is this material new to anyone? Damien? It's okay? Yeah. So the idea here is for you to do those all these tarea in red are the new homeworks. So and by the end of semester, hopefully you'll be handing in those these tareas. There's quite a lot of them. So I suggest that as you prepare the lectures, you do those tareas. The idea is that you hand in a selection of 60% of those tareas. So you don't need to do them all, you just do 60% of them. You choose 60%. That's quite a bit. I mean, there's many little tareas like this. Okay. Okay, so the last thing I want to mention in this introductory section is the Poynting's theorem. Okay, so the idea is to connect with the Lorentz force here. We have that the electromagnetic force or the Lorentz force on a point charge Q is given by V cross B, where V is the velocity of the charge, and the power then exerted on this charge is F dot the velocity of the application point, which would be the velocity of the particle. I have a typo here as well. So okay. We see that the magnetic field exerts no power. When we take the dot product with the velocity, this term cancels out. And so the power exerted on a single charge is just the velocity of the charged dot the electric field. Okay. And so we can extend this reasoning to the power exerted on a continuous distribution of charges and on a continuous distribution of current densities. Okay, so we go to the continuum limit. We no longer think about these point charges. We talk about the continuum of electric charge. Okay, and we have this charge density rho and the electric current density inside some small volume elements dV. Okay, and so the net power exerted by the electromagnetic fields on this volume dV is just the current density dot the electric field inside this volume density. Is this obvious to everyone? I can explain a bit more if it's not.
Professor?
Mm-hmm.
In that case, dB is in volume, right? Not in frequency?
Oh, it looks like a nu.
I'm just asking, yes.
No.
So it's in volume, thank you.
It's just, yeah, that would be the volume. Okay. But is that, I mean, it's the same as writing this electric current is NQ times V dot E. Right. So and that would be the number that's density. Okay. And so the power power for a single charge is QV dot E. That's the power for one charge. And so times n times dV would be the number of charges. Okay. So we have that the total power exerted by the electromagnetic field on the charges inside a macroscopic volume V is just the integral of the dP. Okay, so this will be the power exerted by the electromagnetic fields inside the volume. And the idea here is to connect this power, the power that the power exerted by the electromagnetic fields on the charges. We want to connect this power with the energy stored in the fields, because the idea is that the fields exert work on the charges, but that comes at some cost, you know. And so this is the goal here. We want to know what is the continuity equation for the energy density. And so the idea here is to replace J in the preceding equation. So the one, so we have this expression here for the total power exerted inside the volume with charges. Okay, and we replace in this equation with equation 4 here. So I write J equals curl of H minus the time derivative of D. Okay, and plug it in here. And then you do vector calculus and rewrite that expression. Maybe I should write it down. So that's what I'm trying to say is, so that was the Maxwell equation. And we had, on the other hand, that and so that's and this is what I mean, we can be rewritten in this other way. So for now, it's just a trick. I mean, equation 18 or the one I've just written down are just as horrible. And there's no clear gain at this stage, I must admit. Okay, but you know how it is with this with vector calculus. It's there are lots of tricks, and this is one of them. Let's go on, and we use the induction law, which is this one here, to replace this term, lambda cross E, okay? And then we have that's more interesting. We have that we have a divergence of this term, which is we'll be calling the pointing vector. And this term, like h dot time derivative of b, for a linear medium, this is like the derivative of b squared, okay? And we have here something very similar, e dot time derivative of d. For a linear medium, this also would be the time derivative of e squared, okay? So this is exactly what I'm explaining here. So for a linear medium, this expression h dot time derivative of b is just time derivative of h dot b, or b squared or h squared, depending on how you want to write it. And similarly for e and d with this other term here, okay? And so in the end, we can rewrite this expression for the power exerted inside a medium, identifying these terms here, the pointing vector and the energy density. So the energy density is this term here. So E dot D or E squared and B dot H or B squared. And this is the pointing vector, okay? And okay, so we can define U and S this way. We can put them in equation 20 here. And since this equation must hold for any volume V, it must also hold locally. And we then have equality between this equation, which looks like a continuity equation for this quantity U, in terms of the power exerted on the charges. Okay, so since this is the power exerted on the charges, what's on the left-hand side must be some sort of continuity term for the energy density. Now, I think that this, I'll be making it, yes, no, this is as far as I get here. But I'm sure that you must have seen this before, in the sense that we'll be calculating the pointing vector for a plane wave, and we'll see that S is U times C along the direction of propagation. In any case, I want to know whether equation 23 is familiar to all. Has someone not seen equation 23 before? Okay, so it's fine. I can go on then. Then, in the same way as for the energy conservation, which is seen, so we just saw that the power exerted on the charges can be connected to the fields through the definition of this term U, which would be the energy density, and S, which is going to be the flux of electromagnetic energy, or the Poynting vector. So we can also do the same with momentum. So instead of looking at the power exerted inside a volume, we want to look at the acceleration of charges inside a volume. So we use Newton's second law for the variation of the linear momentum. So that would be the total momentum of charges inside a volume dV. So this delta P mech would be the mechanical momentum. This is the mass times the velocity of all charges inside a volume dV. Okay, so maybe I should write it down. So we have, this is what I mean. So this is the total momentum of charges inside a volume. So we must imagine, a volume element like this. And I'm counting n charges in here. Okay, so that's what I'm trying to do. So when we integrate over all volume elements, and we integrate over, well, d3x would be the volume element in Cartesian coordinates. Okay, I'm using the Lorentz force acting on, sorry. Yeah. Yes, I'm sorry, I got distracted. Yeah, so I mean, equation 24 is the Lorentz force applied to, so this would be d times the sum of pi over dt equals to the sum of all the Lorentz forces, which would be then this rho times E plus rho V cross B times dV. Okay, so you please stop me if there's something that's not clear. And so if I integrate over all volume elements, then I get that the variation of the momentum inside a volume, any volume, is given by the integral of the Lorentz force. Again, we have another tarea here. We use Maxwell equations to replace rho and J. So what do I mean here? I mean this. You use these equations to replace rho and J here. So you say J is curl of H minus dt, and E is divergence of B. Okay. So you replace, where was I? Yeah, so we replace rho and J that way into equation 25. Okay, so I plug in, so that would be J here, rho and V is J, and this is rho. Okay, so I plug in the Maxwell equations, and I can rewrite equation 25 in this other way. So here we have an additional term that is additive to the mechanical momentum, and since it's added to the mechanical momentum, it enters the equation in the same at the same point. I mean, inside the time derivative, we relate this term with the momentum in the fields. Okay, and so the momentum in the fields is given by the volume integral of the Poynting vector. So this is a vector, and so for a component of the moment, and you integrate the same component of the Poynting vector. Okay, and so we associate this with the momentum in the field. So the Poynting vector is connected to the momentum stored in the fields. Okay. And on the right-hand side, we have this horrible term here, which is then the sum over Cartesian components. J goes 1, 2, and 3. Okay. And we have like something like close to a divergence, since we have that we are summing the gradients along each component. And this matrix here is called the tensor of electromagnetic tensions. And so its expression is like that. It's not a diagonal. This is these are the diagonal terms. Well, you know, yes, if sorry, yeah, that's right. It's not a diagonal. It contains off-diagonal terms, and that would be the expression that connects the momentum exerted on the charges with the momentum in the field. So if you want to accelerate something, you need to do it at the expense of the momentum in the fields here. Now we can rewrite this last expression, highlighting the divergence in the electromagnetic tensor. This, I mean, maybe I should write it down on the side. So what I'm trying to say is that we have some overall components times the integral of V this thing here can be written as let me see. So we can write it down as the integral d3x of sum of j and this part here I can write as the divergence of t. I'm not sure how to write this. Probably this notation is very unorthodox. I'm inventing this vector here, which this one. Yes.
The notation there will be nabla j tij.
Is that what you mean?
Yes.
Yes.
Yes, because then the j you sum over the j's and you get like a vector in I, which is the same as which is what you're looking for, because you have a vector in I with the momentum.
Exactly. Yeah. Thanks, Felipe. Yeah, this is exactly where I was meaning to get to, because here I'm using the divergence theorem or the Ostrogradsky theorem. I'm not sure how you know it. That would be then the integral of TA dot Ti. And in this other notation, it's going to be the integral of dA I times sorry. With a sum convention. And this is exactly what we have in equation 29, where this little n would be the unit vector normal to the surface area element. Okay. So the idea here is just to write the conservation of momentum for the fields in a more compact way. But then we've summarized today that we have well, we have introduced the wave equations. We've seen that they fulfill, I mean, that the electromagnetic potentials fulfill the wave equations under the Lorentz condition, and that we can relate the power and the acceleration of the fields onto the charges with the momentum and the energy stored in the fields. Okay, so this is a very brief introduction to waves. And next, we need to look at the propagation of waves in vacuum. So especially the idea of polarization, which is super important in astronomy. Okay. So before finishing for today, I just wanted to bring up the textbook. Where were we? Okay, so we are doing just this. Okay, so this is chapter 2. My summary might be different from what's in Rybicki alignment because I used Jackson electrodynamics. Okay, but it's the same. I mean, I'm not inventing anything here. It's standard stuff. So please, I need you to prepare the lectures, and for Thursday, let's quickly review chapter 2, and very briefly go through it. Okay, the idea is it's quite short. I mean, compared to the first chapter. The first chapter was about like from around 40 pages, and this one is much less. It's around 20 pages also. Okay, so it's we'll just go very quickly through it, and it's important to focus now on the on this idea of quasi monochromatic waves. This is a quite subtle topic, that of polarization, and it's crucial in astronomy. So we'll try to deal with it on Thursday. So please, for Thursday, prepare chapter 2. I'll ask you for your help to quickly go through it. So you don't need to do all of the reasoning here. Now we go faster, okay? And just say, when this section we present the polarization, this is the most important aspect. So check whether anyone needs further explanations. It's okay to say that you do not understand. It's much worse not to say it. Okay, I mean, if you understand everything, then it's okay. You can keep quiet. But if there is something that you do not understand, then it's important to say so, because afterwards it's we can't progress. So please prepare chapter 2. And in terms of the homeworks, the homeworks are the ones I'm giving in the lectures now. We're no longer doing the problems from the textbook. Okay, this is only the ones that I'm giving in the lectures. Good. So with this, I think we're done for today. And please let me know once you've handed in your homeworks for first homework, so I can share the exam. And I will replace the lectures for next week. So this way, I mean, you'll have plenty of time. So don't worry, Nidia and Precious, take it easy. Do your travel arrangements next week, okay? And then meanwhile, Felipe and Andres and yourselves as well can work at your at your pace on the exam. Okay. So with this, let's meet on Thursday then. Okay. Ciao.
Thank you, Professor.
Adios.